Okay, so today we will start the session by understanding the definition of power. So power is the rate of work done with respect to time. So we define power in two sense. Okay, instantaneous power delivered by a force. That is the rate of work done by that force with respect to time. Now we know that the work done by that force is integration F dot ds in general, or in a small time dt, the work done is equal to F dot ds. Okay, so can also be defined as F dot ds by dt, which becomes F dot v. So this gives us a simple formula for instantaneous power by force F, which is instantaneous rate of work done with respect to time. So that given by this simple formula. Okay, now just like we've defined instantaneous power as the instantaneous rate of work done with respect to time, we can also define the average power is the average rate of work with respect to time. Instantaneous power is the instantaneous rate of work done with respect to time, which is this quantity. whereas the average power is equal to the average rate of work done with respect to time. Okay, so having understood that, next thing, the SI unit of power is watt, okay, where 1 watt equals to 1 joule per second. There is also a unit commonly used in engineering, horsepower, or sometimes also called British horsepower. They are one and the same thing. So this is approximately equal to 746 watts. No, it is British horsepower. Okay, next let's understand a question. So consider a projectile particle projected from the ground level at a speed of 25 meters per second at an angle of projection of 53 degrees, let's say. So particle P, its mass is, let's say, 2 kilograms, is projected at time t equal to 0 as shown. So you have to find the instantaneous power delivered by weight mg at t equal to 0, t equal to 1 second, t equal to 2 seconds, t equal to 3 seconds, and the average power from 0 to 2 seconds and from 0 to 4 seconds. Okay. Try this out. Take the value of g as 10 meters per second square. So just try out this question. Okay, so nobody's worked out the values yet. Anybody got the answer? You see, for the first part, for instantaneous power, we have to use the formula instantaneous power is dot product of force with velocity, or that is equal to the rate of work done with respect to time. Okay, so at t equal to 0, the velocity is this one, no? 25 meters per second at 53 degrees. So that is cos 53, you know, is 3 by 5. So 15 I cap plus sine 53 is 4 by 5 plus 20 j cap in meters per second. And the force is nothing but the weight. Okay, very good, Dantesh. And the force we are talking about is the weight. So that is nothing but minus 20 j cap in newtons. So power is minus 400 watts. To just take the dot product of this and this. Now similarly, at t equal to 1 second, the velocity will become 15 I cap plus 10 j cap. We'll use the relation that Vx is equal to u cos theta, which is 15, but Vy is u sin theta minus gt, which is 20 minus 10t in meters per second. And obviously the force we are talking about is same. That does not change with respect to time. So power instantaneous power delivered is okay. Arvinda, this is clear now. Component form. Okay. Now similarly work out the C and D part of the first question. The instantaneous power at 2 seconds and 3 seconds. Tantrish, your answers are correct. Very good. Okay, Anmol, yes, that's correct. So we can see that at t equal to 2 seconds, the velocity becomes 15 I cap. So the power should be 0. And at t equal to 3 seconds, the velocity is 15 I cap minus 10 j cap. So plus 200 watts. Yes, Prince, that's correct. Good. Now let's come to the second part. So second part, we have to calculate the average power. So that is work done divided by the velocity. So in this case, we will calculate the work done as mg dot product with displacement, because mg is a constant force. Okay. So from 0 to 2 seconds, okay, how to calculate the displacement? So you can see x is u cos theta t, which is 15t, which will become 30 meters. Okay. Y is u sin theta t minus half gt square, which will be 20t minus 5t square, which for 2 seconds will become 20 meters. So the displacement will be 30 I cap plus 20 j cap in meters. So work done, force is nothing but the weight, which is minus 20 j cap in newtons. So this one's dot product with this one will give us the work done as 20 into minus 20, so minus 400 joules. So from that we will see that the average power is this much. Okay, so similarly, the work done in 4 seconds will be 0. Ansh, very good. So to calculate the the average power prince, we have used this formula, na? Total work done upon time. So from 0 to 2 seconds, to calculate the total work done, we need to find out the displacement. So the displacement is coming from this formula. X component is u cos theta t, y component is u sin theta t minus half gt square. So in this, you put the value of time as 2 seconds. Na? So it will come out to be 20 meters. This will come out to be 30 meters. So once you got the displacement, from that we calculate the work done by taking the dot product and then divide the work done by the time taken. So that's the average power. Okay, good. Now same way you have to do for the B part also. From 0 to 4 seconds. What about the displacement? So when you calculate the displacement, it will come out to be 60 I cap. When you calculate it, you'll see it will come out to be this. So the work done will come out to be 0. So the average power will come out to be 0. Dot product, beta. Do not forget the basics, na. Dot product of two vectors क्या होता है? Ax bx plus ay by. So if I'm doing f dot s and the f is basically mg. So mg as a vector is what? Minus mg j cap. And this one's dot product I'm doing with x I cap plus y j cap. I will get minus mgy na. ये तो आप पहले भी सीखे हो वर्क डन में. हाउ टू कैलकुलेट द वर्क डन बाय ग्रेविटी. Learn this now. Okay. Let's do another example. So this time, this block is at rest at time t equal to 0. And this is a rough surface. It has coefficient of friction 0.2. Now we start pulling the block at t equal to 0 with a constant force like this. So a constant force F of magnitude 50 newtons at 37 degrees horizontal starts acting on the block. Now the mass of the block is suppose 10 kilograms. from t equal to 0 onwards. Find the instantaneous power by each of the forces acting on this block at the instant t equal to 2 seconds, and find the average power by each force from 0 to 2 seconds. Okay, so let's look at the working of this question. Correct. So the first thing we have to do is find the acceleration of the body, from which we can find the velocity. So if we divide this force into components, F cos theta and F sin theta, you can see that F was 50 and theta was 37. So this component will become 40 newtons and this component will become 30 newtons. Then the weight of the object was 100 newtons, 10 kgs. Okay. So the normal reaction, that will become 70 newtons, and that means the kinetic friction acting will become 0.2 into 70 or 14 newtons. So the body's horizontal acceleration will be such that this so 2.6 meters per second square. So for the first part, we can see that the velocity of the body at t equal to 2 seconds so in general, we can write the velocity like this. Okay. So at t equal to 2 seconds in particular, it will be 5.2 I cap in meters per second. So at t equal to 2 seconds, the velocity vector will be like this. It will be 5.2 meters per second. So now you can see all the forces. This is at 37 degrees. Kinetic friction is like this. Normal reaction is like this, and mg is like this. So instantaneous power delivered by each of these forces we can calculate like this. Yes, that's correct, Tantrish. These two, and then power delivered by normal reaction will be zero because normal reaction is perpendicular to the instantaneous velocity. Power delivered by mg will also be zero. For the second part here, I will just use a simple trick. Instead of doing the whole calculation, average power is going to be equal to work done upon time. So work done is going to be dot product of force with displacement upon time. So this can also be written as force dot average velocity, because displacement upon time is average velocity. Now this is a uniformly accelerated body, which means that the average velocity is this. Okay. And at t equal to 0, the initial velocity was 0. So therefore, at t equal to 2 seconds, the average velocity is 0 plus v by 2. So it is just half of what it was earlier. So it is 2.6 I cap in meters per second. So I don't need to recalculate anything over here. So I can see that the average power by force F will be just what the instantaneous power was. Okay. The average power by friction will be half of what the initial value was. So that is, so I can use this trick from kinematics. Yeah, Prince, after getting the V average, ना, we take the dot product ना. So अभी देखो dot product जब ले रहे हैं with the V average, everywhere the V average is half of the V that we got in the first part ना. So the work done should also become half. I mean the power should also become half. Okay. So the idea is that, see, because U was 0, okay, and V was equal to, how much was it? 5.2 I cap at t equal to 2 seconds. Okay. Therefore, V average was V by 2, no? So therefore, the work done by each of these, sorry, the instantaneous power and the average power is, so it is half of the instantaneous power. So that's how I'm directly using that, okay, to get these two values. So that's the trick I was telling you about. Instead of calculating the displacement, calculating the work done, and then dividing by time, I don't need to do so many steps, because I know that the average velocity will be just half the instantaneous velocity at 2 seconds. So average power will be force dot product with average velocity, whereas instantaneous power was force dot product with instantaneous velocity. So that relationship will be 1:2. Is it clear now, Prince? Okay. Now next thing we'll understand is that from work kinetic energy theorem, we know that net work done is equal to change in kinetic energy. Okay, finish writing now. Okay, so this is done now. Let's move on to this next thing. So as I was saying, we have learned earlier from work kinetic energy theorem that net work done is equal to change in kinetic energy, or in a small time dt. Okay. this will be small change in kinetic energy. Okay. So rate of net work done with respect to time will become rate of change of kinetic energy with respect to time. So this is the net power instantaneous, okay, that equals to the rate of change of kinetic energy with respect to time. Okay, so to understand this point, just think of a particle going in a curved path like this. So at any point of time, its instantaneous velocity and its instantaneous acceleration will have a relationship like this, where if this angle is theta, you can see that E sine theta is the normal component of acceleration and E cos theta is the tangential component of acceleration, which is dv by dt, change of speed. And this is the centripetal acceleration. That is the logic of this statement actually. Okay, so if a number of forces are acting on a body, then its rate of change of kinetic energy, that will be equal to the net power delivered by the forces. That is, this will become like this. Yeah, this is the definition of tangential acceleration. And tangential acceleration is the component of acceleration along the instantaneous velocity, because the instantaneous velocity is always along the tangent to the curve. The direction of instantaneous velocity at any point will be along the tangent to the path. If the particle's path or trajectory is like this, then whatever is the direction of the tangent, the instantaneous velocity is along that direction. So the component of acceleration which is along the tangent, so this is the tangent at that point P. This is the normal. So the component of acceleration along the tangent, that is called the tangential acceleration. And that is equal to rate of change of speed, as you know in kinematics. In circular motion also you studied this, no? Yeah, that's tangential acceleration. E subscript T. This is the symbol used for the tangential acceleration. So this is the component of acceleration along the velocity or along the tangent. Yeah, I mean that's why they are equivalent, na, actually. You can see that's why the equivalence of this means that again it's showing you that relationship, that the tangential component is E cos theta, which you understand geometrically also. So this net power theorem, that net power is equal to net instantaneous power is equal to instantaneous rate of change of kinetic energy, that's a consequence of this statement here itself. Okay, so this is all about power. So with this, we complete all the concepts of this chapter, work, power, and energy. So now, next session, we will be doing discussion of H.C. Verma questions. Tomorrow only for us. Okay. So discussion of H.C. Verma exercise problems from work, power, energy chapter. And next week, we will look at the module questions also. So please start working accordingly. By next week, you have to complete the problems of both H.C. Verma and the module. And after that, the next chapter of physics we will do Will be a new section. We'll be moving out of mechanics now, and we'll be discussing heat and thermodynamics. Okay, that's it for today's session, people. Wish you all the best.